Good evening. My name is Jabran Ali, and this is my final project presentation for the course EEL6562. The name of my project is Using Image Processing Techniques to Estimate the Health Status of a Leaf in MATLAB. In this project, what we do is we use an image processing technique which uses the concept of the RGB model along with a particular concept developed in the paper we use for reference, which is also being mentioned at the end of the slide. And based on that particular concept and image processing techniques, we've developed an algorithm and we implement it using MATLAB. Now, the details of which will be explained now. We know that every plant has got leaves which have got certain nutrient contents. The nutrient contents of every leaf is reflected in terms of its chlorophyll content. Now, the visually perceptive nature of the chlorophyll content is the greenish nature of the leaf. Now, the amount of the chlorophyll content or the nutrient content will basically define the health status of the leaf. So, what we do is we develop a certain mathematical model based on several trial and error methods to find out the chlorophyll content, in turn the nutrient content, as a result the health status of a leaf. And this is done by several trial and error methods, and we use a particular mathematical concept. The usefulness of this project. Now, in any agricultural country, especially a developing agricultural country like India, the agriculture is like the backbone of the economy. It contributes around 18.6% to its GDP according to the statistics in 2005. MATLAB will basically produce or provide a very cheap and a robust method of arming the farmers using this by implementing this particular software tool, and this will basically have a serious impact on the way the agricultural process is being taken out or carried out in a country, growing developing country like India. And it will also have further usefulness that will basically impact or equip the farmers. By using this tool, you can increase the output of the crop and find out a better estimate of whether a crop is healthy or not healthy. And by using this tool, you can increase the output of a crop, and you can use it in a very efficient manner in your agricultural process. So it found a very interesting and important application in the agriculture industry, especially like a growing developing country like India. Now, RGB model. The RGB model basically, it's an additive model. Any color is basically has red, green and blue colors, parameters for any pixel values. Now if RGB model basically works on additive nature, different values of R, G and B when mixed will basically give me different colors, different proportion, mixed and different proportionally would result in a broad range of colors. Also, another property of this model is that if R, G and B, if mixed in equal content, equal proportion, that is if R equals G equals B, the color obtained is white. So this is the image processing concept which was used. That is, we extract the RGB values for every pixel content in the leaf, and the applications of an RGB model is like it is used in generally photographic equipment, sensing equipment, display systems such as electronic systems, TV, computer. This slide shows the RGB model. If we mix red and blue, we get magenta. If we mix red and green, we get yellow. If we mix blue and green, it gets cyan. If we mix R, G and B, that's red, green and blue in equal proportions, we get the color white. Excuse me. Now, previously, the chlorophyll content was found out by monitoring the chlorophyll contents of the leaves of various plates by using different chemical means or chemical mechanisms and different chlorophyll meters. That is how we could find out the chlorophyll content of a leaf in different stages shown in this particular palette. So this from increasing chlorophyll content, and you see here the chlorophyll content is decreasing. These are chemical methods of finding out the chlorophyll content in leaves. Now the content which is the concept which is being developed in the research paper which we reference uses a different method, that is uses image processing concept. What from we look from in this table is that we calculate the correlation coefficient of the RGB values over different periods of time. So for different combinations of R, G and B. Now this slide is basically further explained in the next slide. What basically we use is we have a leaf, and by chemical methods we know the chlorophyll content of each pixel in it. So we extract the RGB values of each of the pixels, and for each of the pixel on A we find out the R minus B, that is we find the difference of the red value and the blue value of the pixel, and we find the chlorophyll content, because that is already found out from the chemical mechanism. From there we plot for a particular day, say for example on 20th April. 20th April is represented by circular dots, and this is being plotted. Now we do the same thing on a different day, and this is done and plot on a particular day, and this is done over 5 different days. As a result, we get a series of dots showing the different chlorophyll content which is already given from the different RGB values. From this particular plot we find out the best fit graph. The best fit graph is shown by this particular line, and the equation of this best fit graph is y equal to 0.796 minus 0.00813x, where x is R minus B and y is the corresponding chlorophyll content. Now with respect to this equation of line which is obtained, the correlation coefficient while using the concept of R minus B is minus 0.76. Now this is a very good estimate or mechanism of finding the chlorophyll content by using only R and B values, and especially of using the function of R minus B. But this only gives us a good correlation coefficient only on particular days and only in certain environmental conditions or meteorological conditions. But on other meteorological conditions or days, the correlation coefficient is very poor. As a result, this is a trial and error method, and this is basically performed for different values. So a first instance we find out the chlorophyll content if we use only R values, G values, R upon R plus G plus B, and similarly these are the different combinations which have been tried out. This has been tried out for 5 different days, and we find out the correlation coefficient for 5 different days. We add it up, find the average, and from here we see that for R minus B values, the correlation coefficient is very high, but on different meteorological days it's not that high, it's very poor, it's 0.76. Ideally we need the correlation coefficient to be 1, so we keep on with our experimental process. The second process which is being showed here is the R minus B upon R plus B values. So we scan the entire leaf, take out each pixel has its own RGB values, we find the difference of R minus B and R plus B for that particular leaf. This is the input. From there we know the chlorophyll content of the leaf, and we plot it in this graph, and we do this for 5 different days as shown here, that is 20th April, 21st April, 18th May, 24th May and 7th June, and then we find the best fit curve for this mechanism. We're using R minus B on R plus B, and the resultant equation of the line which we obtain is y equal to 0.952 minus 1.76x, and the correlation coefficient obtained is minus 0.81. Now this is a very good correlation coefficient, it's very close to 1. This wasn't obtained, this we didn't see in the previous case, and from this particular slide we see that for R minus B and R plus B, this is the highest correlation coefficient, that is the closest to 1, which has been obtained when we average out for all the 5 days. So we reach the conclusion that this is the mathematical formula or tool which, or the equation rather, will be used to extract the chlorophyll content of a leaf. And we use this and in MATLAB. What we do is, this is the evaluation phase of the project, where we establish a particular flowchart to run or implement the mathematical concept we just developed. Now, it uses a particular main function shown by this particular part, and this particular function is known as a subroutine. Now, this I'll be showing in MATLAB. Now, from this particular part of the slide, we use for the project a healthy leaf and an infected leaf. The healthy leaf and both the infected leaf has the same uniform background of a brown color. Now, the leaf is basically, over a period of time, undergoes a process. Could be due to aging, viral infections, fungal infections, or ruining of the crop due to insects. The chlorophyll content or the nutrient content is reduced. So this is the leaf, the infected leaf, where the chlorophyll content is less, and this is also visually perceptible. Now we take these two leaves with a similar background and we run them and we read it into the MATLAB simulation which I'm about to show. So this here is our main function and I'm about to run the MATLAB simulation. So here what we do is, and from here we see, and MATLAB is running. From here we see that we read in the healthy leaf, and this new function, which is a subroutine, here we extract the leaf, the image of the leaf, we initializes the values to 0, and from here we see this particular for loop scans the entire image, and for each pixel value. Now when it's actually scanning the values, here this particular function IMPixel basically extracts the RGB values and stores in a matrix P. Now if this is a particular condition, remember the brown background of the leaf shown in this particular slide? This brown uniform background is a condition such that which has RGB values of its pixel as 251, 255, 255. So if the pixel values are brown, then the resultant chlorophyll content is 0, because we are not taking into consideration of the chlorophyll content of the background. If that's not the case, we basically, from the pixel values which we obtain, the RGB values of the pixel, which is basically a matrix, we find out the first P1, which is R, P3 is just B, and we find out R minus B upon R plus B. This is the golden ratio of the optimum function which we had calculated by the trial and error method explained previously. So this is what we obtain. Now this value which R is obtained, we input it into this function which we had obtained, the equation of the line, and from there we find out the chlorophyll content of that particular pixel. Similarly, we scan the entire leaf using this particular for loop and find the chlorophyll content of each pixel. As a result, what happens, all these values are added up and the summation will give me the total chlorophyll content of the leaf. Similarly, similar performance is done on the infected leaf. Similarly, again we take the infected leaf shown by this particular picture, read in the image, call the function, then extract the RGB values, initialize. If we get the pixel values of the brown or the background as 251, 255, 255, we get the chlorophyll content as 0. Otherwise, we again calculate the R minus B upon R plus B, and similarly the chlorophyll content of the leaf. Then we add it all up and get the sum. So we are basically, what we are doing is we are finding out each of the pixel values, for each of the pixel value in the leaf, finding R values and the B values, and then we are finding the chlorophyll content of each pixel based on this particular mathematical formula which was developed in this particular concept, and then we are doing this for all the pixels in that particular leaf, eliminating the background or the uniform background, and adding all the chlorophyll values will basically give me the chlorophyll content of the leaf. Ironically, even the chlorophyll content of the leaf is basically visually perceptible as the greenish nature of the leaf. In establishing this particular golden rule or the golden ratio, there is no mention of the green pixel value. Now this is the output which we see. This is the workspace where all the matrices were established, and the sum1 which we had obtained, as you can see in the main function, the sum1 is basically giving me the chlorophyll content of the value of the pixel of the healthy leaf, the total chlorophyll value, and then sum2 will basically give me the chlorophyll content of the entire leaf for the unhealthy leaf or the infected leaf, which is obviously going to be less than the healthy leaf. And then at the end we do a ratio in implemented MATLAB is sum1 upon sum2 upon sum1 into 100, and this will basically give me the health percentage of the infected leaf, which in this case has come out to be 97%. So this is what our MATLAB project establishes. Now this research or this concept was developed by the two researchers, Japanese researchers, Kawashima and Nakatani, and we had used, or rather I had used this, but their research paper to establish this to research paper, and I had developed the MATLAB code and the flowchart and the algorithm, and basically implemented it using MATLAB by doing study on the research carried out by these two scientists. Now they had used this concept of coming up with an algorithm that comes up with the chlorophyll content of the leaf, and as a result, as I said, something like this is very different. You use a particular MATLAB tool and a MATLAB a software simple tool which is cheap, and and it could have a very great impact and finds an application in the agriculture industry, and a developing country like India, where the agriculture industry is still growing and forms a majority of the backbone, especially in its GDP. This was one of the important reasons which inspired me to actually choose this particular project. And this project was very interesting because using image processing concepts and developing a mathematical model, you actually find out the chlorophyll content of a leaf, and it has an application in industry where it could be so much beneficial to the farmers, so where it could efficiently help them for yielding a better crop by finding out the healthy nature of the leaf and making their day-to-day agricultural life easy and find a place in the agriculture industry if used. And it is a very economic and efficient to use, and also very cheap and robust. So based on this concept developed by these two researchers, I was successfully able to come up with a flowchart and an algorithm and implement it in MATLAB and simulate in MATLAB, and the advantage that could have a possible impact or application in the agriculture industry that could actually help the farmers to yield better crop and also find some considerable use in the agriculture process and industry. And as mentioned previously, I had used the research paper by these Japanese researchers, and these are the references being used, the project being used here. The notes of Dr. Wu, my professor, was being used in this particular presentation and project, and of course the reference project and the referred book. Thank you.